Neptune, the distant blue planet at the edge of our solar system, somehow gives off more energy than sunlight it absorbs, like it's secretly burning from within. It's a strange, almost surreal scene, a world chilled to icy blues on the outside, but alive with hidden warmth beneath the surface. Why does Neptune radiate so much extra energy? What's happening deep inside this icy giant that keeps it glowing brighter than we'd expect? Stick around, because unraveling this cosmic mystery reveals a surprising story about the forces working beneath the planets we think we know. Overview of Neptune as a gas giant. Neptune is a fascinating planet, primarily classified as an ice giant rather than a classical gas giant like Jupiter or Saturn. Its atmosphere is composed mostly of hydrogen, helium, water, ammonia, and methane ices, hence the term ice giant. Unlike the larger gas giants, Neptune has a relatively smaller core surrounded by thick layers of compressed ices and gases. Visually, Neptune appears as a striking blue sphere, thanks largely to methane absorption, which gives its atmosphere its distinctive hue. Its cloud tops are frigid, with temperatures plunging well below freezing, creating a stark contrast to the heat we often associate with planets closer to the Sun. Despite its extreme cold surface temperatures, around -200 degrees Celsius, Neptune radiates more energy into space than it receives from the Sun. This may seem counterintuitive at first because, being farther from the Sun, one would expect it to be a cold, passive sphere. However, the planet's internal processes are more complex. The core of Neptune, composed of rock and metals, is believed to be under immense pressure, generating heat through radioactive decay and gravitational contractions. This internal heat source continually supplies energy to the planet's outer layers, causing its atmosphere to emit more radiation than the Sun's rays deposit. As a result, Neptune's thermal emission is substantial, and this glow can be detected by telescopes from Earth, even in the harsh darkness of space. The physical structure of Neptune contributes to this energy excess. Its heat mainly originates from residual heat left over from its formation, as well as ongoing internal processes like convection within its thick, icy layers. This convection stirs heat from the interior upward, causing energetic weather phenomena such as high-speed winds and large storm systems. The planet's internal heat flux is roughly twice what you might expect if it simply reflected sunlight, resulting in a planet that radiates energy at levels that seem disproportionate to its cold exterior. This internal heat creates a visual contrast between the cold, icy outer atmosphere and the surprisingly warm, dynamic interior. It's a vivid reminder that planetary heat balances are often more about what's happening beneath the surface than what's visible on top. Neptune's position in the solar system. Neptune resides at the very outer edge of the solar system, more than 30 astronomical units away from the Sun. Its position places it in a region where sunlight is incredibly faint, dimmer than what reaches Mercury or even Mars, let alone Earth. Despite this, Neptune emits more energy into space than it receives from the Sun, a fascinating anomaly driven largely by its placement and internal processes. The distance means that the solar energy reaching Neptune is just a fraction of what the inner planets soak up, so the planet's internal heat sources become the dominant factor behind its energetic glow. The vast distance from the Sun creates a stark contrast between the cold vacuum of space and the planet's own heat production. In outer space, temperatures plummet to hundreds of degrees below freezing, making Neptune one of the coldest planets in the solar system. Yet, despite these frigid conditions, Neptune radiates more than twice the energy it absorbs from the Sun. This excess energy clarifies the fact that external solar heating is negligible, and internal heat becomes the key contributor. Its position in the solar system essentially acts as a barrier. Dusts and gases here trap and retain internal energy without significant replenishment from solar insolation. The brightness we see from Neptune isn't because of solar warmth, but due to warm, convective activity deep within. Because it's so far from the Sun, the planet's internal heat, generated by gravitational contraction, radioactive decay, and residual heat from its formation dominates its thermal emission. This internal heat causes large storm systems and dynamic atmospheric activity, which can be observed as bright clouds and turbulent weather patterns. The high-energy emissions we detect come primarily from these internal processes rather than external sunlight, creating a vivid contrast between the icy cold environment surrounding Neptune and the planet's surprisingly energetic interior. In essence, Neptune's distant circumnavigation of the Sun acts as a natural shield, shielding it from solar warmth and allowing internal heat to shine through more prominently. It's like a thermal engine working in the dark, radiating heat that's trapped beneath layers of icy grip. Its position amplifies the intrigue, making Neptune a heavenly example of how planetary energy budgets don't always follow intuitive patterns. Instead, they reveal complex interplays between location, internal dynamics, and the slow aging of a planet in the cold abyss of space. The concept of planetary energy balance. Neptune, the eighth planet from the Sun, is a fascinating example of how celestial bodies can defy simple expectations about heat and cold in space. Despite being so far from the Sun, receiving a tiny fraction of the star's energy compared to Earth, it radiates considerably more energy than it absorbs. This apparent paradox hints at complex internal mechanisms that generate heat within the planet. Essentially, Neptune's energy output exceeds its input, leading it to glow faintly in infrared wavelengths. This excess energy radiates out into space, creating a visual contrast. The cool darkness of its outer atmosphere juxtaposed against the subtle, persistent warmth that the planet emits. The idea that planets maintain a delicate balance between incoming and outgoing energy helps explain this phenomenon. For planets like Neptune, the small amount of solar energy it receives is dwarfed by the internal heat sources. Over billions of years, residual heat from formation, radioactive decay, and gravitational contraction all contribute to a planet's internal heat reservoir. Neptune's internal temperature is thought to be much higher than predicted just from solar heating. Its thick atmosphere acts almost like a giant hot water bottle, radiating the heat away into space. This process creates a vivid visual contrast. On one hand, the icy exterior, perpetually frigid and coated in methane clouds that reflect sunlight, while on the other, the faint infrared warmth escaping, a reminder of hidden internal activity. Unlike Earth, which maintains a more or less balanced energy budget due to active weather systems, the heat emerging from Neptune's depths is a product of ancient and ongoing internal processes. The planet's internal heat is thought to originate from gravitational energy released as the planet gradually contracts under its own gravity, along with the slow decay of radioactive elements deep inside. This energy source sustains vigorous atmospheric activity, including storms and high-velocity winds. These phenomena are driven by the planet's internal heat, not just the weak sunlight that reaches Neptune's distant orbit. As a result, Neptune appears to be a glowing, restless giant, radiating about twice the energy it captures from the Sun, creating sharp visual and thermal disparities that captivate astronomers. In essence, Neptune exemplifies how a planet's internal processes can dominate its energy budget. The planet's heat emission is not just a reflection of residual warmth, but an ongoing testament to its internal dynamism. It highlights how celestial bodies are more than mere recipients of solar radiation. They are active worlds with concealed thermal engines powered by multiple sources. This differential between what Neptune receives and what it radiates offers vivid insight into planetary evolution and the ongoing dance of heat and cold in our solar system. The planet's persistent infrared glow is like a faint heartbeat, echoing the deep, hidden forces shaping its nature. Solar energy absorption by Neptune. Neptune sits at the edge of our solar system, roughly 30 astronomical units from the Sun, where sunlight is a faint whisper compared to what we experience on Earth. Despite this, Neptune manages to soak in a tiny amount of solar radiation, but interestingly, it radiates far more energy back into space than it absorbs. This discrepancy has always fascinated astronomers, leading to questions about what kind of processes keep the planetary heat engine running. Sunlight that reaches Neptune illuminates its thick, icy atmosphere, causing some surface features to glisten faintly, yet the direct heating is surprisingly minimal, roughly 1,000 times weaker than the sunlight we experience on Earth. Still, the planet's upper atmosphere absorbs these scant photons, warming up just a little, creating a delicate balance between incoming and outgoing radiation. But the story gets more intriguing behind the scenes. Neptune's atmosphere and interior act like a giant heat reservoir, releasing energy on their own accord. Even though the sun's infrared radiation barely kisses its clouds, Neptune's own internal heat, generated through slow gravitational contraction and radioactive decay, rises to the surface and escapes into space. This internal heat supports the planet's dynamic weather systems, including high-velocity winds and massive storms, like the famed Great Dark Spot. What's remarkable is that this internal heat exceeds the energy Neptune receives from the sun, sometimes by nearly double. The planet essentially energizes itself from within, glowing faintly with its own heat, creating a stark visual contrast. Icy, cold exterior versus a simmering internal core. From a visual perspective, the difference between the cold emptiness of space and Neptune's vibrant atmospheric activity is striking. Despite being so far from the sun, Neptune radiates warmth relative to what it absorbs from solar energy. If we could peer beneath its thick cloud layers, we'd see an environment that's hotter than expected for such a distant world. The planet's internal energy drives complex atmospheric phenomena, fueling winds that can blow over 1,000 miles per hour, far faster than Earth's strongest hurricanes. While the surface temperatures are extremely cold, often below -200 degrees Celsius, the heat emanated from within can create a subtle glow that makes Neptune radiate more energy than solar absorption alone. This ongoing internal heat process keeps Neptune slightly warmer than the vacuum of space around it, resulting in the net energy surplus that scientists have come to understand as a defining characteristic of its thermal profile. In essence, Neptune's quiet but persistent internal heat keeps it glowing faintly, masking the coldness of its distant, sunless environment. The tiny amount of sunlight it absorbs is simply not enough to sustain its observed thermal emission. Instead, Neptune relies heavily on ancient, residual heat stored deep inside. The balance of these energy flows makes it an inviting puzzle, highlighting how planetary worlds can sustain vibrant activity far from the warmth of their star, relying instead on their own internal fires to keep the cosmic dance going. Internal heat sources in planets. Neptune, unlike many planets that mainly emit energy just as much as they absorb from the sun, shines brighter in the night sky than sunlight alone can explain. This phenomenon hints at powerful internal heat sources fueling its glow. The origins of this internal warmth are rooted deep within the planetary interior, where complex processes generate heat that escapes gradually through the planet's layers. Unlike Earth, which has a relatively moderate amount of internal heat due to radioactive decay, Neptune's internal heat is extraordinary, making it a glowing beacon of leftover planetary formation energy and ongoing internal dynamics. One of the main contributors to Neptune's internal heat is residual heat from its formation. When Neptune coalesced from the swirling nebula of gas and dust, immense gravitational energy was converted into heat. Over billions of years, a significant portion of that heat has yet to fully dissipate. This leftover heat provides a continual source of energy, slowly escaping through the planet's thick atmosphere and deep interior layers. Additionally, radioactive decay within Neptune's rocky core also produces heat, albeit at a lesser scale compared to residual formation energy. Together, these processes keep Neptune's atmosphere warmer than expected for its distance from the sun. Another intriguing aspect is the role of internal convection. Inside Neptune, heat rises from the hotter core areas toward cooler outer layers, creating convective currents that transport thermal energy outward. These currents enhance heat transfer from within the planet, contributing to its overall luminosity. The deeper, hotter layers of Neptune radiate energy through the gaseous mantle, giving the planet a kind of internal cape of warmth that can be visualized as a gentle, steady glow. This convection process is similar to what happens inside stars, but on a much smaller and more controlled scale, continually fueling Neptune's faint but persistent outflow of energy. Furthermore, the presence of helium and other heavier elements in Neptune's interior influences how heat is transported and retained. These elements contribute to the planet's density and affect its heat capacity, helping to trap some heat for longer periods. This dense, layered interior acts like an insulating shell, preventing heat from escaping too rapidly. As a result, Neptune's internal processes are sustained over vast spans of time, making the planet a peculiar cosmic furnace. The contrast between its icy exterior and the surprisingly energetic interior makes Neptune a fascinating example of how planetary bodies can retain and dissipate heat against the frigid vacuum of space, reminding us that planetary warmth isn't solely about proximity to the sun, but also about the fiery heart beating inside. Composition and structure of Neptune. Neptune's inner makeup is a layered mosaic of ice, rock, and metallic elements. Unlike the gas giants, Neptune isn't composed mainly of hydrogen and helium, but instead has a core made up of heavier elements including rock and metal, weighing several times Earth's mass. Surrounding this core is a thick mantle of icy substances, water, ammonia, and methane, that give Neptune its characteristic blue color. These ices are not frozen solids like ice cubes, but exist under immense pressure and relatively high temperatures deep within the planet. This composition results in a dense, somewhat fragile shell that is very different from the gaseous atmospheres of Jupiter or Saturn. What makes Neptune's structure particularly intriguing is how these different layers interact energetically. The core, sitting under tremendous gravitational compression, generates heat through processes like slow contraction over eons and radioactive decay. The icy mantle acts as both an insulator and a reservoir of internal heat, trapping energy that gradually seeps outward. Unlike a simple cold ball of ice, Neptune keeps internal heat stored within its depths, which then finds its way to the surface. The planet's icy and rocky interior is less transparent than gases, so this heat remains partially trapped, eventually radiating into space as infrared energy. A visual contrast emerges because the outer atmosphere is composed mainly of hydrogen, helium, and methane gases, which reflect sunlight and give Neptune its mesmerically vivid hue. Yet, beneath this serene appearance, the planet is a cauldron of warm heat sources. The internal heat flux is stronger than what sunlight delivers. This imbalance is striking. While Neptune's upper atmosphere is extremely cold, at around -200 degrees Celsius, the planet radiates more energy than it receives from the sun. This extra heat is believed to originate from its interior layers, which are still slowly cooling and contracting. The planet's distinctive heat emission might be compared to a warm glow within a cold shell, a contrast that makes Neptune one of the most energy-efficient worlds in our solar system. In essence, Neptune's composition and layered structure create a natural heat engine. Its dense, icy core and insulating mantle store energy that leaks outward over billions of years. This process sustains the planet's atmospheric activity and contributes to its unexpected excess energy emission. Because of this layered complexity, Neptune appears to glow in infrared wavelengths more brightly than the sunlight it absorbs, an impressive feature rooted in its intertwined, multilayered makeup of cold, icy materials and hot interior processes. Heat retention in ice giant planets. Neptune, along with Uranus, is classified as an ice giant, a type of planet characterized by its deep layers of heavy elements such as water, ammonia, and methane ices. Despite being so far from the sun and receiving only a fraction of the solar energy that Earth's atmosphere does, Neptune emits more energy into space than it absorbs from the sun. This intriguing phenomenon is primarily due to the planet's internal heat sources and the way it retains this warmth over billions of years. Unlike terrestrial planets, Neptune's thick atmosphere and massive interior act like a giant thermal reservoir, holding on to heat much more effectively than previously assumed. The core of Neptune is thought to consist of a dense mixture of rock and metal, surrounded by an extensive layer of ices, substances that, under the immense pressures and temperatures deep inside, exist in exotic states. As the planet formed, gravitational energy was converted into heat. Over time, this heat has slowly trickled outward, but the process is incredibly inefficient because of the planet's high internal pressures and the insulating properties of its thick gaseous envelope. Imagine trying to cool down a hot cup of coffee covered by a thick layer of foam. Heat remains trapped longer because the insulating layer slows its escape. Similarly, Neptune's thick atmosphere acts much like that foam, preventing heat from escaping quickly into space. Another significant factor is Neptune's ongoing internal heat production, which differs from planets like Earth. On Earth, radioactive decay within the crust generates heat, but for Neptune, the primary sources are residual heat from formation and slow contraction processes. As the planet contracts tiny amounts over eons, gravitational energy is released as heat. This process, known as Kelvin-Helmholtz contraction, effectively keeps Neptune warm from the inside out. The planet's ability to retain this internal heat leads to high temperatures in its interior, which, in turn, produce a dynamic and active atmosphere bombarded with storms and high-energy weather phenomena. These internal heat sources are what make Neptune glow faintly with warmth, even at such a remote distance from the Sun. In essence, Neptune's capacity to radiate more energy than it receives directly from the Sun is a window into the complex and dynamic nature of its internal structure. It's a delicate balance of ancient heat, slow gravitational settling, and the insulating effects of a thick gaseous envelope. This internal heat drives many of the planet's striking visual features: swirling storms, bright cloud bands, and mysterious eruptions. It reveals a planet whose internal life is still simmering quietly, long after its formation, showcasing a fascinating contrast between the icy cold of its outermost layers and the hidden heat below. Neptune's internal heat generation mechanisms. Neptune, the eighth planet from the Sun, stands out because it radiates more energy into space than it receives from the Sun. This imbalance has intrigued scientists for decades, prompting deep questions about what powers this distant world's internal heat. Unlike Earth's surface temperatures, which mostly reflect solar heating, Neptune's internal heat source is substantial enough to produce a glow that outshines the energy it absorbs from sunlight. To understand why, it's essential to explore how Neptune generates and sustains this internal heat. A key driver of Neptune's excess heat lies in its ongoing internal processes that produce energy deep within the planet. Unlike a simple ball of gas, Neptune has a complex interior structure with layers of hydrogen, helium, and heavier elements. This layered composition allows for different mechanisms of heat production. One significant process involves the slow process of gravitational contraction. Over billions of years, Neptune's initial formation resulted in a dense core surrounded by a thick envelope of gases. As the planet slowly contracts under gravity's tug, potential energy converts into heat, much like when a star contracts during its formation. Although this process is gradual, it continues to produce some heat even now, contributing to the planet's overall warmth. Another mechanism involves the phase transitions of materials within Neptune's interior. Specifically, the high-pressure environment causes some of the hydrogen to enter a metallic state, highly conductive and capable of generating heat through dynamic processes. As these metallic hydrogen layers undergo changes and turbulence, they can produce friction and heat internally. These materials act like natural dynamos, generating magnetic fields and releasing heat in the process. This continuous mixing and convection keep the interior stirred up, releasing heat outward in a process somewhat akin to boiling water, but on a planetary scale. Lastly, the planet's internal heat is sustained by residual heat from its formation. Neptune formed from the dust and gas left over after the sun's birth, and not all that heat escaped into space. Over billions of years, while most of the initial heat has radiated away, some remains trapped in the dense interior. This residual heat acts as a slow, persistent glow emanating from deep within Neptune's core, radiating outwards through convection processes. The contrast between this internal warmth and the frigid cold of the outer atmosphere creates a striking visual. Bright, wispy cloud patterns against a backdrop of deep blue, illuminated by heat rising from within. These processes collectively keep Neptune hotter internally than it would be if it solely relied on solar energy, giving the planet a mysterious, dynamic character that intrigues astronomers and curious minds alike. The role of radioactive decay. Deep beneath Neptune's swirling clouds, a quiet but persistent power source contributes to its unexpected heatfulness: radioactive decay. Unlike the cold, distant appearance of the planet's icy exteriors, its interior holds a simmering secret. Radioactive elements like uranium, thorium, and potassium are embedded within Neptune's rocky core, slowly breaking down over vast stretches of time. This process releases energy in the form of heat, which doesn't radiate outward immediately but accumulates within the planet's dense layers. This phenomenon isn't unique to Neptune, but becomes particularly significant because of the planet composition. The core, enriched with radioactive isotopes, acts much like a natural nuclear furnace. As these isotopes decay, they produce heat that gradually warms the surrounding material. The heat then migrates outward, convecting through the planet's interior. In Neptune's case, this internal heating surpasses the energy it absorbs from the sun, pushing the planet to radiate more energy than it receives. It's as if Neptune is kind of a giant, slow-burning cosmic heater, fueled by radioactive material buried deep inside. Visually, this internal heat manifests in ways that contrast sharply with the cold expanse of space. While Neptune's outer atmosphere remains frigid, hovering around -218 degrees Celsius, its core remains relatively warm, thanks to radioactive decay and residual heat from its formation. This discrepancy creates a heated interior beneath a starkly cold exterior, leading to turbulent weather patterns and high-speed winds within the planet's atmosphere. The entire process highlights how radioactive decay acts as a continual, internal power source that sustains planetary warmth long after the planet's initial formation. Ultimately, radioactive decay is a slow but steady engine behind Neptune's excess energy. It's like a cosmic hearth inside the planet, smoldering beneath layers of icy clouds and swirling storms. This internal heating, born from the decay of heavy atoms, keeps Neptune radiating more energy than it takes in from the sun, showing how even in the cold outer reaches of the solar system, radioactive processes can maintain a surprising degree of internal warmth. Kelvin-Helmholtz contraction process. Neptune's surprising excess of radiated energy compared to what it absorbs from the sun is largely explained by the Kelvin-Helmholtz contraction process. Think of it as Neptune slowly shrinking in size over vast timescales, releasing gravitational energy as heat in the process. Unlike Earth or Jupiter, Neptune isn't just passively reflecting sunlight. It's actively generating its own warmth through this slow, yet persistent contraction. The planet's interior is so dense that gravity pulls its mass inward, causing slight but continuous compression. This process is akin to a giant cosmic balloon shrinking just a tiny bit every million years. As Neptune contracts, potential energy stored in its massive, gaseous layers converts into thermal energy. The heat generated during this contraction seeps outward through the planet's thick atmosphere, creating a persistent internal heat source. This heat is what we detect as Neptune's excess thermal radiation, more heat leaving the planet than it receives from the sun. The contrast is striking. Neptune's outer layers are often cold and distant, bathed in faint sunlight, but beneath the clouds, a fiery interior quietly warms the planet from within. The rate of contraction isn't rapid. It occurs over incredibly long periods, billions of years. Yet the effect accumulates enough to sustain Neptune's heat emission. On the scale of planetary physics, this slow, shrinking acts like a cosmic engine, continuously transforming gravitational potential into heat energy. Scientists estimate that this process accounts for roughly half of Neptune's total thermal emission. The planet's thick atmosphere acts as a thermal insulator, trapping this heat underneath, which slowly escapes into space as infrared radiation. This ongoing internal heating sustains high-altitude storms and dynamic atmospheric phenomena, even in the cold vacuum of space. In essence, the Kelvin-Helmholtz contraction process forms the backbone of Neptune's energetic profile. It turns the planet's gravity and mass into a long-lasting heat source, offsetting the coldness expected if it only relied on solar energy. This process has a visual appeal as well. Imagine a giant, slow-squeezing ball emitting its own internal glow, creating a stark contrast against the icy, distant blue hue of Neptune's atmosphere. So, even with a distant sun, Neptune's energetic heartbeat is sustained by its own gravitational muscles gradually tightening its gaseous layers, reminding us that planets are not static, but dynamic entities driven by profound cosmic mechanics. Comparison with other gas giants. Neptune stands out among the gas giants partly because it emits more energy than it absorbs from the sun. While Jupiter and Saturn also radiate excess energy, the reasons behind Neptune's energetic glow are particularly intriguing. Unlike its larger cousins, Neptune's internal heat source is more concentrated relative to its size, and this makes its emission of infrared radiation quite intense. This excess energy is visible in its bright, bluish appearance, which hints at complex internal processes beneath the icy clouds. Despite being much farther from the sun than the inner planets, Neptune still radiates a significant amount of heat. Jupiter, for instance, emits about twice as much energy as it receives, thanks in part to gravitational contraction and ongoing heat from its formation. Saturn radiates roughly 50% more energy than it absorbs, owing to residual heat still escaping from its core. Neptune's excess, however, is surprisingly high. It radiates roughly 2.6 times the energy it receives. The disparity hints at powerful internal heat sources that continue to shape its environment, even as the sun's influence wanes with distance. Visual contrasts between Neptune's cold exterior and its internal heat make the phenomenon remarkable. Its outer atmosphere hovers around -218 degrees Celsius, appearing cold and distant. Yet beneath that icy veneer, heat from the planet's interior persists. This heat flows outward, driving weather systems like the high-speed winds that can reach up to 100 kilometers per hour. These winds help distribute internal heat, creating dynamic atmospheric phenomena that seem almost in defiance of the frigid environment outside. The contrast between the chilling outer layers and the warm core creates an energetic, tumultuous atmosphere that makes Neptune a fascinating study. Comparing Neptune with Jupiter and Saturn highlights distinct internal mechanisms. For Jupiter, leftover heat from its formation and gravitational contraction dominate. Saturn's excess energy partly comes from the slow cooling of its dense core, releasing gravitational potential energy over eons. Neptune's case is more complex. It's believed that radioactive decay and residual heat generated during its formation, combined with less efficient heat loss due to its composition, keep it radiating strongly. This sustained energy emission is why Neptune, in many ways, feels like a cold but lively world, shimmering in infrared light that betrays its hidden internal warmth. Observations of Neptune's heat emission. Neptune's heat emission is a fascinating anomaly that has puzzled astronomers because the planet radiates significantly more energy than it absorbs from the sun. Unlike terrestrial planets, Neptune's average temperature is around -200 degrees Celsius, so sunlight contributes only a tiny fraction to its overall energy budget. Instead, What makes this planet glow with internal heat is a mysterious process that scientists are still trying to fully understand. When instruments like infrared telescopes observe Neptune, they detect an intense glow of infrared radiation emanating from the planet's atmosphere and interior. This glow indicates that Neptune is shedding a tremendous amount of energy into space, roughly twice the amount it receives from the Sun. These heat emissions are quite visible when comparing the brightness of Neptune in the infrared spectrum to its appearance in visible light. While visually a cold blue orb, in the infrared, it appears much brighter due to its internal heat escaping. This visualization helps distinguish the colder surface temperatures from the planet's warmer interior layers that radiate energy outward. The fact that Neptune radiates more energy inward than it absorbs means that it must be generating this heat somehow from within, likely through residual heat from its formation and ongoing gravitational interactions. To put it simply, Neptune is like a massive, distant campfire smoldering deep within its cold exterior. The observations from spacecraft, particularly Voyager 2 and more recent telescopic data, confirm that Neptune's internal heat is substantial. Voyager 2 measured an infrared flux several times greater than what the planet could be receiving from the Sun. This excess energy isn't just drifting away harmlessly. It influences Neptune's atmospheric dynamics, driving powerful storms and high-velocity winds. The heat causes the upper layers of the atmosphere to be more active than the distant, frigid environment would suggest if it were solely warmed by sunlight. Imagine the contrast, a planet bathed in icy cold, yet steadily leaking heat as if it's still radiating from a fiery core deep within. That internal warmth creates a visual symphony, cold blues and icy whites juxtaposed with flickers of internal heat visible in the infrared spectrum. What keeps Neptune radiating so much energy remains an ongoing scientific inquiry. Some theories suggest it's still cooling from its initial formation, slowly releasing leftover heat. Others propose that gravitational interactions with its moons or internal convection currents contribute to this heat flow. Observing Neptune's heat emission allows scientists to piece together the planet's internal structure and evolution. The clear contrast between the planet's subdued appearance in optical light and its energetic infrared glow paints a vivid picture of worlds where cold exterior shells hide fiery, dynamic processes beneath. It's like peering into a frozen lake and seeing a warm glow underneath. An intriguing reminder that many celestial bodies have layers of complexity hidden beneath their calm appearances. Implications for Neptune's atmosphere and weather. Neptune's ability to radiate more energy than it receives from the Sun is a fascinating anomaly that has significant effects on its atmospheric dynamics and weather patterns. Unlike Earth, where sunlight largely drives atmospheric phenomena, Neptune's internal heat source acts as a powerful engine stirring up turbulent weather systems. The excess energy emanates from the planet's interior, composed of residual heat from its formation and radioactive decay, which keeps heat flowing outward. This continual release of internal heat creates a temperature differential between the planet's interior and its colder upper atmosphere. The result is a striking contrast: warm, active regions beneath the clouds and cooler, calmer layers above, fueling intense cloud activity, storms, and jet streams. This surplus energy manifests visually through dynamic cloud formations and large storms that can evolve rapidly. Neptune is renowned for its high-speed winds, some reaching over 200 miles per hour, far exceeding what sunlight alone could power. These winds are driven by the heat escaping from within, creating a system of convective cells that stir the atmosphere incessantly. Such heat-driven convection leads to turbulent weather that constantly reshapes cloud patterns. Bright, white clouds often appear in regions where hot gases rise swiftly, contrasting sharply against the darker, cooler background of the upper atmosphere. Even in areas of the planet seemingly shrouded in cold, the internal heat keeps underlying layers active, producing a lively and ever-changing sky. The ongoing release of planetary heat also influences the formation of storm systems similar to, but far more immense than, storms on Earth. These storms can be seen as dark spots or bright whirls moving across the planet's face. Unlike terrestrial weather, which is mostly seasonal, Neptune's weather shows remarkable variability driven by internal heat fluctuations. The internal heat might drive cyclical intensifications or waning of atmospheric activity, resulting in periods of calmer skies punctuated by violent storms. This creates a planet that appears perpetually in motion, a swirling mosaic of heat-driven phenomena, echoing the deep-seated energy reservoir within Neptune. Finally, the interaction between heat and cold enhances the visual contrast of Neptune's atmosphere. Cold, outer layers reflect much of the planet's thin sunlight, producing a deep indigo hue. Beneath this, the interior heat rises, warming certain zones and producing striking bright clouds or storm features that stand out vividly against the darker background. This contrast reminds us of an immense, cold ocean stirred by unseen fires from within, a place where heat fuels chaos, and the weather is a symphony composed by the subtle balance between internal warmth and frigid outer space. Significance of Neptune's excess energy. Neptune's ability to emit more energy than it receives from the Sun is a fascinating anomaly in planetary science, especially considering its position so far from the Sun, where temperatures are supremely cold. Unlike planets closer to the Sun, Neptune is shrouded in icy winds and frozen gases, yet radiates a significant amount of heat into space. This excess energy isn't just a trivial detail. It acts like a beacon revealing the planet's internal heat engine, hinting at dense, dynamic processes occurring deep within Neptune's structure. The primary significance of Neptune's excess energy lies in what it tells us about the planet's internal composition and history. Unlike Earth, where surface heat mainly comes from radioactive decay and residual heat from formation, Neptune's excess warmth suggests the presence of ongoing heat sources deep inside. This could be due to primordial heat retained from its formation, much like a slow-burning ember tucked deep within it, or ongoing processes like gravitational contraction. Essentially, Neptune is still cooling down, but it's doing so very slowly, releasing a steady stream of heat that helps maintain its thick, turbulent atmosphere. This energy keeps strong winds blowing across the planet's atmosphere, often reaching hundreds of miles per hour, and fuels enormous storms like the Great Dark Spot. Visual contrasts make this heated reality more striking. While the planet's surface and atmosphere appear bleak and icy, the heat emission creates an almost ghostly glow in the infrared spectrum, an internal fire hidden beneath layers of cold. If you could see Neptune in infrared light, the faint, warm glow would reveal a planet that radiates roughly twice the energy it receives from the Sun. This means Neptune's internal heat is comparable to, or even surpassing, the heat it absorbs. This energy flow shapes the planet's weather system, sustains complex cloud formations, and influences its magnetic field. Understanding Neptune's excess energy deepens our grasp of planetary evolution, especially for ice giants. It challenges simple models of how planets cool over time. Instead, Neptune seems to have an internal heat reservoir, possibly fueled by leftover gravitational energy from its formation or layered processes involving icy components melting and refreezing beneath the surface. This ongoing energy release is critical for explaining why Neptune remains one of the most turbulent and active worlds in our solar system, despite being so cold on the outside. It's as if Neptune's hidden core keeps whispering of an ancient, simmering core long after the initial planetary formation, making it a planet of ongoing internal drama and energy. Broader impacts on planetary science. Neptune's ability to radiate more energy than it absorbs from the Sun challenges basic assumptions about planetary heat sources and influences how scientists view the evolution of distant worlds. Unlike terrestrial planets that mostly rely on solar heating, Neptune's internal heat plays a significant role, causing the planet to glow faintly in infrared wavelengths. This excess energy isn't just a quirky anomaly. It offers clues about the planet's internal composition, heat generation processes, and evolutionary history. The discovery that Neptune emits roughly twice as much energy as it receives stimulates curiosity about how such distant giants sustain their internal heat over billions of years. Visual contrast between the frigid cold of space reaching Neptune's outer atmosphere and the comparatively warm interior create a fascinating puzzle. While the upper atmosphere could be as cold as minus 214 degrees Celsius, the planet's deeper layers are believed to be significantly hotter, possibly reaching several thousand degrees. These internal heat flows drive vigorous weather patterns and colossal storms, like the Great Dark Spot, similar to Jupiter's Great Red Spot, but more mysterious. Understanding the mechanisms behind this heat flow helps scientists refine models of planetary atmospheres and predict climate behaviors on other icy giants and exoplanets. The broader impacts ripple into planetary science by reshaping models of planetary atmospheres, interior dynamics, and even magnetic field generation. Because heat flow profoundly influences magnetic fields, Neptune's surprising internal heat contributes to its unexpected magnetic properties, which are tilted and offset from its rotation axis. This understanding expands our knowledge of planetary dynamo processes, a core aspect of planetary geology and magnetism. It emphasizes that distant planets may share more internal complexity than earlier assumed, encouraging scientists to develop better tools for studying planets in our solar system and beyond. Ultimately, Neptune's excess radiance acts as a beacon, guiding researchers in uncovering the hidden life stories of worlds far from the Sun and broadening our vision of what makes a planet truly dynamic. So, to wrap it up, Neptune surprises us by radiating more energy than it absorbs from the Sun, thanks to internal heat sources like leftover formation heat and ongoing gravitational interactions. This creates a fascinating contrast. While the deep space around it is icy cold, Neptune's insides are surprisingly warm, glowing with the energy it generates from within. It's a vivid reminder of how dynamic and mysterious our solar system truly is, even for worlds that seem so distant and frozen. If you found this glimpse into Neptune's heat intriguing, just imagine what other secrets the outer planets might be hiding. Stay tuned for more adventures into the cosmos, where each discovery sparks new questions and wonder. Thanks for joining me on this journey. There's so much more out there waiting to be explored.